What if we learn to get good grades then?
Where'd you get that skirt from?
Okay, this is our first lesson in vector calculus. Now, if you look at tonight's homework, basically it's going to be one worksheet per night. So look how easy this homework is. This is review.
That's what you always
Okay, you know what? Let me give you an example. Let's say you have a position vector. Okay, cosine t, sine t, t. Now, you guys are used to two-dimensional parametric equations, but now, of course, we're doing three. Somebody tell me, besides Joe, if I were to graph this in space, what is the path traced by the particle?
Straight line.
No.
a sphere.
If these were linear, like that one's linear, but if these two were also linear, then it would be a straight line. No, it's not a straight line.
Sphere. A cylinder.
Oh, cone.
You're getting closer.
Cone.
A helix.
Okay, I told you not
A
besides Joe.
helix.
Okay, in two dimensions. Okay, in two dimensions. What if you had this in two dimensions then?
Really hot.
Sine t. Now, I hope you guys understand that, you know, when we study parametric equations in PCH and in BC calculus, this means the same thing as x equal cosine t, y equals sine t. Maybe if you think about it that way, see, this gives you the position of the x coordinate and this is the position of the y coordinate. So how do you find the path that's traced out by the particle? You eliminate the parameter. Now normally what you would do is you would solve for t in one equation and plug it into the other. But when you have trig functions, normally you would use identities to eliminate the parameter. So what identities can I apply to this? Remember when you took PCH and we did parametric equations and we told you that if you get stuck, you should try this technique?
Square.
Square the equations. If you square the first equation, you get this. Square the second equation, you get this. So if I want to eliminate the parameter, in other words, get rid of the t, what do you think I'm going to do with these two equations? Add, subtract, multiply, or divide? You add x squared plus y squared equal 1. Hey, you want circle of radius 1. So the particle is traveling on the circle. Now, do you guys remember how to figure out how the particle travels on the circle? You make the chart. You make, no, not number line. You make the chart.
That wasn't always like plus minus plus.
No.
No.
No chart.
No chart.
Okay, so what you do is you go back to the original equations and then you compute the position of the particle at these different values of t. So when t is 0, plug it back into these equations, what's the position of the particle? Cosine of 0 is 1. Sine of 0 is 0. So the particle starts here. We call this the initial position of the particle. Does that sound familiar? Okay, pi over 2. Plug in pi over 2 to the original equations and you get
0
and
1.
1. So if t is measured in seconds, pi over 2 seconds later, a particle is here now. Okay, what about at pi? Park.
-1.
And 0. Okay, so the particle is here at pi. 3 pi over 2, when?
0, negative.
Oh, you guys think you're good now?
Yeah.
What about 2 pi? I'll do it, 1, 0. Oh, so the particle starts here, let me see your part. And it goes like
Let
this.
me see your.
And if you keep going, it just keeps doing this. And in physics, what do we call this?
Infinite loop.
Uniform circular motion. So these are the equations of uniform circular motion. Now, what we're going to do on tonight's homework is we're going to do calculus on these vector functions. So if this is, and we did this in BC, but you guys probably forgot. So if this is your position vector, how do I get the velocity vector? Please remember? You take the derivative. Park, take the derivative of each of these components.
Negative sine t cosine.
Negative sine t, cosine
Oh, I
t.
remember something.
And then, of course, we can compute the acceleration vector. How? Acceleration is simply the derivative of velocity.
Negative cosine, negative sine.
There you go. So at any value of t, we can figure out the velocity and acceleration vector. So, what about at t equal pi over 2? When t is pi over 2, we already know the position is 0, 1. You guys know what position is, where the particle is. So right there, that's the position. Right when t is pi over 2, what is the velocity vector? So here, velocity vector at pi over 2. Can you guys plug in? Go. Wang.
Velocity at pi over 2. Shoot. -1.
These are quadrantal angles, people.
0.
So that means when t is pi over 2, Joe, you should be listening because in physics you're going to learn this.
Okay.
So that means at pi over 2, the velocity vector has an x component of -1 and a y component of 0. That means it looks like that. Does that sound familiar from physics?
Yeah.
When you have uniform circular motion, the velocity is always tangent to the circle.
Hard to do that math in physics.
Yeah, but see, when you're taking what, just regular physics?
Isn't it?
AP Physics 1.
Yeah, that's regular physics then, yeah?
Oh my
No.
god.
You just have to know, you gotta memorize stuff like, you gotta memorize that the velocity is always tangent to the circle.
Hey,
But no, we don't have to. Once we know the equations, we just figure out the velocity and acceleration vectors.
wait, what's tangent to the circle? Sorry.
The velocity vector.
Is
This is review of physics right here.
tangent to the
Tangent to the circle, at the point of tangency. It's always gonna be tangent to the circle.
so like
So in other words,
The ball.
right here, the velocity vector would look like that. See how it's tangent to the circle?
only at those numbers, yeah.
No,
No,
look right here would look like that then, it would be tangent to the circle.
Okay.
Remember when you let go of the string of the ball, it goes straight. It's like that.
Okay, now let's do the acceleration vector at pi over 2. I didn't realize we're gonna work at this damn space here, but we are. Pi over 2, plug in pi over 2 into the acceleration vector, and what do we get?
Is that so?
Acceleration vector.
0.
0,
-1.
-1. So Monsieur Park, when time is pi over 2, the acceleration vector has an x component of 0 and a y component of -1. That means it looks like this. Here's the velocity vector, there's the acceleration vector. Does that remind you of uniform circular motion?
Kind
What did your physics teacher teach you about uniform circular motion? Joe,
What? I have high. Oh wait, that
of.
doesn't.
Yeah.
why didn't you say it louder for the video?
Wow, we didn't get.
Okay, then you should be listening. The velocity vector will be tangent to the circle, but the acceleration vector is centripetally inward. Does that sound familiar? We did this in PCH.
Wait, is this in PCE?
Yeah,
I know it's just BC.
when we did parametric equations and then we took derivatives of it.
Oh, the way
Oh,
to
but see, we can compute velocity and acceleration vectors. It doesn't matter what the equations are. So this is just a two-dimensional example, but tonight's homework you got three-dimensional examples.
Oh no.
No. Okay, so let's take a look at this one now. Let's see if anybody remembers anything from PCH. Joe, just in 2 dimensions. Oh, we already talked about it. So this is uniform circular motion, but then what if I add a z component to it? So in the xy plane, it just goes around like this, but then now we have a z coordinate. So every second, the particle rises 1 unit above the xy plane, so it goes like this.
Oh, so you have a string.
Yeah, but what's the scientific name for this, like this? What is this?
Slinky.
No. Cho said it 5 minutes ago. It's called
Helix.
helix.
Double. What's it called?
Double helix.
That's
DNA? Yeah, but this is just a single helix.
Yeah.
So like that. Wang, 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 wang. It's a helix. Okay, now tonight's homework, you're gonna be computing velocity and acceleration vectors. That's super easy. Just take derivatives, and then you gotta compute the length. Wait, let me see.
How many questions?
Wait.
Just 5.
No, you just gotta. We're not even computing length. Cho. Oh, that was 2 sections from now. Oh, this is just nonsense, man. Nonsense. Look how easy this is. So, what would the velocity vector of this be? Quick.
Negative. Sine t
Cosine.
cosine.
Cosine t,
1.
comma 1. What's the acceleration vector gonna be? Negative cosine t, negative sine t, 0. Bam! There you go. And then, of course, you can compute it at any value of t just by simply plugging in. Now, tonight's homework, I don't see any problems. Look at number 2. Let's just look at number 2 for the people that are not here. Position vector is t minus sine t. Oh, you dummy. 1 minus cosine t pi. Now, we learned this in PCH. Just look at the x and y component only. If I were to just graph that in the xy plane, what is the path traced out by the particle? Oh, we did this in PCH. Ha! You get first crack at it.
Helix.
No, it's two-dimensional.
Double helix.
Yeah,
It's
time
still
out.
2-dimensional.
Time out. We're doing a two-dimensional thing. So a
Okay.
helix is a three-dimensional figure.
Cylinder.
Okay, you keep on going with the three-dimensional figure. It's two-dimensional.
A circle.
Okay, at least that's a good, that's a two-dimensional figure. But
No way.
no, this is the circle, remember? If you just had, that was the example we did. This is the circle. So this one is not a circle. Wayne, second crack.
Ellipse.
Oh, it's a line.
Hyperbola.
Okay,
Line.
no, okay, I'll give you a hint, maybe this will.
What is this
If you were to graph this on your
Oh,
calculator,
it's the,
it goes like this.
the pedal thing.
Roses.
Oh, just
No.
kidding.
A cycle.
Pedal thing.
There you go, it's called a cycloid. Now, how do you get a cycloid? What if you have a circle,
Oh,
and then here's a point on the circle. Now, here's a point P on the circle. What if I roll the circle without slipping on this line? What is the path traced out by the
It's a
particle?
cycloid.
It's gonna go like this. If you roll the circle without slipping, it's gonna look like this. We call that a cycloid. You guys remember that from PCH, or is that gone from the memory?
What else from Vsauce?
From what?
From Vsauce.
Oh, yeah.
I don't know what that is. Now, what's so important about a cycloid? I taught it to you guys in PCH, but no, I want to just forget everything. If I invert the cycloid upside down like this, I think Mr. Rubash taught you guys this too.
He did.
Why don't you say that louder for the video?
I don't know. I didn't know.
Okay, what if you were to, okay, let's say we have a contest. We have a physics contest. You are to build a ramp. Okay, here's point A.
Oh, you said that.
Yeah, here
It's
is
a lower,
point
it's
B.
straighter.
We are going to build a path. We're going to release a ball bearing here. And the fastest to get from A to B is going to be the winner. So do I just build a ramp like that?
Oh,
No, you gotta-
No, you're going to lose.
You gotta make it steep first.
You build, exactly. The ramp is an inverted cycloid because at the beginning, look, it's like a vertical drop. And it goes like this. Wham! So it's already been mathematically proven. The fastest path to get from there to there under the influence of gravity is a cycloid, inverted cycloid. Another property of the cycloid is, what if you have a marble here and a marble there, and you release them at the same time? Who gets to the bottom the fastest?
Same
The
time.
They both get there at the same time. That's another property of the cycloid. So that's why we study it. So in this particular problem, in 2 dimensions, that's a cycloid. But now we have a Z.
Oh, so it's a
tell me.
oh,
So what's the graph now?
it's a half helix.
What?
It's like going.
Okay, look.
Wouldn't it be like,
Okay.
Isn't it the same
Wouldn't it be
but at
anti-
like z equals pi?
Okay, look.
Yeah.
Without this, look, take away the pi. Now we're in 2 dimensions. The graph looks like this.
Wouldn't it be the
Right?
same thing we just?
Now what happens if I add, now notice that's a constant. It doesn't change. So like if z was t, then the thing would start coming out like this. Yeah? But this is just a constant. Z stays pi all the time. So what does that mean?
Like out of the.
Yeah, so you come out pi on the z-axis, and you just do this.
Oh, because it stays constant.
It's a cycloid in a different plane though. See, this is in the xy plane, but then once you put this in, then it's in the plane z equal pi.
What's the name?
It's a cycloid. It's just in a different plane.
Okay.
See, this is a cycloid in the xy plane, but then now you gotta come pi out, and then you get the cycloid in the plane z equal pi. Yeah.
What if the pi was a t, like and like it,
Then it would look like this.
No, but then what would they?
It would get farther and farther from the xy plane.
Wouldn't it be a cycloid just
Wait.
on that plane?
It's on.
Me too.
I'm showing you the graph.
Will there be a name? Is there a name? For
Yeah, I
that?
thought that was a fish.
I don't think there's a name for that. So, but see, that's the thing. You guys got to be able to, visualize three-dimensional, or at least make drawings so that you can understand what's going on.
Okay.
Okay, so tonight's homework, this is just nonsense. I thought we were going to actually compute the length of the position, or the length of the particle travels, but that's not for a while. Now, I also want you to notice that there's answers underneath. These are not my answers again. Now, these are answers from students that actually wrote it down, and I just copied it off the board. So I don't know if they're correct. We need to figure out if they're correct.
How do you do number 4?
You can remember that's BC. You integrate term by term.
Term by term and just.
Okay, here, why don't we just do number 4 on the board? No, you know what? You guys need to do it. You can integrate each of the. So when you integrate a vector function, you just integrate each of the components from 0 to 3.
And
then that's your answer.
But then you put
So like, okay. Okay, I'll just do the first one for you. Okay, so the problem number 4 says, compute the integral from 0 to pi over 3 of the vector function dt if the function is, secant t, tangent t. Ooh, that looks familiar. Of course, on the test, I'm not going to give you this easy kind, Tangent t. Probably going to have to do like partial fractions or something like that. Okay, so if I want to integrate this vector function, you just integrate each of the components from 0 to 3. Okay, I'll do the first one.
secant t.
We integrate secant t, tangent t, dt from 0 to pi over 3. So what's the antiderivative of secant t, tangent t? Secant t from 0 to pi over 3. Using the fundamental theorem of calculus part 2, you get 2 minus 1, 1. So your answer would be 1.
Comma something.
Yeah, and then so basically
Okay.
you just integrate each of the components from 0 to 3.
Not bad.
So what are we doing then? We're just doing vector calculus. You have a position vector or any kind of vector, you can take derivatives of it and you can also integrate them, each of the components. It's very simple. Okay, now